Alright, Wildcats. We've learned some lessons tonight. Lesson number 1. When recording a video for your students or anyone else, please make sure that your microphone switch is not muted. Lesson number 2. Once ensuring that your microphone switch is not muted, make sure your headset is Unit 9. Take 3. Alright, Wildcats. Unit 9, we're going to be talking about exponential and logarithmic functions. These are opposites of each other. The big thing about exponential and logarithmic functions is you guys are constantly saying, when will I use this in the real world? Exponential and logarithmic functions are the primary things that nature is modeled after. Pretty much anything in nature, from the population of jackrabbits in a specific square mile of a forest, all the way down to the microorganisms living within your body, can be modeled with an exponential or logarithmic function. It's absolutely fascinating how nature does this. Today, though, we're going to only be talking about exponential growth. So there's 3 things we're talking about in this unit: exponential growth, exponential decay, and logarithmic functions, and how they all work together or sometimes even against each other. So for exponential growth functions, today we're going to be looking at a couple of things, including how to graph them. And I know after saying that, the first thing on a lot of your guys' minds is, yeah, we're going to have this slide, the slide that everybody loves. However, this time there is something nice. So, that B that always gave us trouble, that horizontal stretch or compression, it does technically exist with logarithms. But we call it something else, it does something else, and we don't worry too much about it. The A on the outside still exists, still the same thing. The H and the K are still vertical and horizontal shifts. So if you need to copy this down again, feel free to do so. You can pause the video and catch back up with us as soon as you're done. Again, keep in mind that this horizontal stretch and compression here, not going to need those two. So let's talk about what an actual real-life exponential function looks like. Not the theoretical one from the previous slide, but what an actual exponential function looks like. Here's what you're going to see. A times b to the x minus h plus k. Now, just like before, a is our vertical dilation factor. Yeah, I know I've only called it that a couple of times. We're pretty much just going to call it a for exponential graphs, but do remember it does represent our vertical stretch. In this case, b is going to be our base. You're going to hear a lot in this unit, make sure your bases match, or make sure your bases are the same. Your H is going to be your horizontal shift, how far left or right this graph is moving. And as always, K is going to be your vertical shift, how far up or down it is. You'll notice that these work almost exactly like everything from before. Up, down, left, right, stretch, compress. You're done. I do want to pay special attention to domain and range this unit though. It was the problems that we missed the most frequently on the Unit 8 test. Good job on that one, by the way, guys. Y'all rocked it. But since domain and range was an issue last time, let's take a special look at it here. First of all, the domain of all exponential graphs is all real numbers, period. End of story. It is not possible to have an exponential graph that has any other domain but all real numbers. Do keep in mind though that there's a lot of ways to write that. And you need to be able to recognize all the different ways to write it, whether it's in set, interval, inequality notation, or if it's just a fancy looking R. Make sure you can recognize all real numbers. Range is a little bit different, but it is simpler than some of the previous ranges we've talked about. In an exponential function, there's only 2 possibilities. Either the graph bends up at which point your range is going to be y is greater than k. That'll mean the a value is positive, or your graph's going to bend down. And if it bends down, then that means your range is going to be y is less than k. K being the number on the outside, or you can also just view k as being your horizontal asymptote. They're going to be the same thing in this case. Again though, do keep in mind that even though I've told you it's y is greater than k or y is less than k, that's just the inequality way of writing it. There's still the set notation, there's still interval, there's a lot of ways we can write this. Make sure you can recognize it when you need to. So, some of the problems on your homework assignment, they're going to give you a graph, like this one. And then they're going to say, what's the formula? So if they give you a graph like this, and they say, give me the formula, we're going to use a relatively simple process to get it. Notice first of all, in the top right there, or top left, they tell you what B is. They're going to give you B. After you notice that they've given you B, you're going to find the asymptote. In this case, they've even drawn it. Where is that horizontal dashed line? Well, they've not only drawn the horizontal dashed line, they've actually said y equals 7. So y equals 7. 7 is your k. Next thing to do is notice that they've given you a point. -5, 5.1. That point we're going to call a reference point, and it's going to be h, k plus a. So the x value is your h, and the y value is k plus a. In this case, since we've got -5, 5.1, your h is -5, and k plus a is 5.1. Notice though that doesn't actually tell you what a is. But since we already know what k is, and we know that k plus a is 5.1, then that means 7 plus a is 5.1. That means if you subtract the 7 over to the other side, you get a equals -1.9. So this graph should open down, and it should have a horizontal asymptote at 7, and it should have a reference point at -5. Check. The last thing we need to do is substitute those values into our formula. F of x equals a times b to the x minus h power plus k. Well, what's our a? -1.9. What's our h? -5. And what's our k? 7. And then again, b, they gave it to us at the very top left, in this case 8. So let's just take that formula and plug it in. A is -1.9, b is 8, h is -5, but remember, the negative is also in the formula, so negative h gives me +5. And then we have +7 on the outside for our k. They gave you a graph, we've given them the formula. That's all there is to it. However, it's not all there is to exponential growth problems. There is also another type of exponential formula, which we call the rate formula. You could write an exponential function like this. Now I know this looks very different, but it's actually the same. Instead of having an a, we have a p. Instead of having a b, we have 1 plus r. And then you could have a modification to the t and then a k at the end, but this problem doesn't have that. So what these letters actually mean is this. P is the principal. It's the starting value. So if you're starting with 3 rabbits, P is 3. If you're starting with 100 bacteria, P is 100. Whatever you start with, that's your P. R stands for rate. Now they're almost always going to give you the rate as a percentage, but in this formula you have to plug it in as a percent. So if they say growing at a rate of 15%, you don't put 15 in for R, you put 0.15. You divide by 100. Move the decimal place to the left twice. Finally, T stands for time since starting. Now it can be minutes, seconds, hours, it depends on the problem, but it's always going to be time. If you're going to graph this, you're usually going to have to replace it with X, because again, Desmos is too dumb to know that you actually mean a variable. So you have to put in F or X. Let's take a look at one of your actual homework problems that uses this formula though. So let's say we're talking about the population of a small town of 15,000 people. Population is growing by 5% per year, and the town can only support 27,000 people, so we need to know how long it'll take to get there so that we can make sure that the town is able to support more than that by the time we reach that. This is actually something city planners do every single day. HRW is going to ask you to enter the function, and they're going to give you 4 different graphs to pick from, and you'll have to pick the right one. Using that graph, make a prediction. Round your final answer to 2 decimal places. Guys, that's incredibly important. I'm always coming around and you guys are saying, I need help, I don't understand why this problem's wrong. Then I look at it, you've done all the math right. You've gone through the whole problem and everything is perfect. But you didn't read the last sentence of the problem, and the reason it's saying you're wrong is because you forgot to round. Or if you did round, you rounded to the wrong number of decimal places. So make sure you're looking at that very last sentence. Now, for this problem, we have to start by asking ourselves, what's the starting value? Well, the current population of the town is 15,000 people. The next question we ask ourselves is, what is the rate? How much is it growing by? Well, they've told us that that's 5%, which again, we change to a decimal, moving the decimal place over twice or dividing by 100 to get 0.05. That means we can write our formula. 15,000 times 1 plus 0.05 raised to the t. Do keep in mind, you could add that 1 and 0.05 to get 1.05. That's fine. That's not a problem at all. That's how I would personally normally write it. The last thing that we need to recognize is they're asking for a specific amount of time to get to a specific number, and we need to identify that number. In this case, 27,000 people. So, here's what we're going to do. We're going to graph the formula. 15,000 times 1 plus 0.05 raised to the t. Notice my scale. On the x-axis, I'm actually only going from about 5 to about 20. But look at my y-axis over here. This thing's going from 15,000, I chose that number because they told me that's where it was starting, all the way up to 30,000 at the top. Since they told me I was trying to reach 27,000, I chose 30,000 as a good go-between. For these types of problems, guys, you have to get familiar and have to get comfortable with changing your window, changing the scales independently. You can't just zoom in and out, because you notice my x values don't go very far. They only go from 0 to 20. But my y values go all the way from 15,000 to 30,000. If you just try to zoom in or out, you're never going to be able to see the numbers you need to see. So make sure you're comfortable just reading the problem and getting the window that you need. Now in this case, I graphed the 15,000 times 1 plus 0.05 raised to the t, and then I recognized that the number we're trying to get to, well, I can just represent that by a horizontal line, and when we get to it, we get to it. So I also graphed y equals 27,000. That's what that blue line there is. So the red line is the formula that we calculated, the blue line is y equals 27,000, and where they cross is the amount of time it takes us to get to that many people. In this case, 12.047 years. I can plug that into HRW and be done, right? Round to 2 decimal places. 12.05. So it's going to take 12.05 years, basically a year and about half a month, in order for us to go from our current population of 15,000 to the maximum town population of 27,000. So we've got just over a decade to make sure that we expand our infrastructure so that we can continue growing properly. Well, Wildcats, that's all I got for you. That's everything you need to be able to finish the homework problems in section 9.1. And when you open it and you look at it, you're going to see that it's only 10 questions. I'm also giving you today, tomorrow, and Friday to do it. That's 10 questions in 3 days. You guys got this. Good luck, Wildcats.